Hello everyone, welcome to EE914 and EE920C. In this lecture, we are going to walk through the behind the scenes of how a Baremetal RISC-V program is compiled and linked to become an executable binary file. Let's start with something simple, a program that blinks an LED light. This is the embedded version of the Hello World program. This might look intimidating at first, so let us break down the elements in there. First, we define some macro functions and variables. In embedded programs, for most of the time, we are going to be interacting with memory mapped registers to control the IOs. Followed by that, we write our first actual line of C program. We define GPI open as a constant, and also a global variable called counter. Then, we define the delay function. For now, you can ignore how this delay works in detail, and just know that when calling it, it will halt the program for some amount of time. Finally, we move to the main function. Inside the function, we first enable the GPIO output functionality, and then proceed to an infinite loop. Inside the loop, we toggle the LED pin every time the loop restarts, delay for 1,000 ticks, which is roughly 1 second, and then increment the counter. Now let us dive into the build process. There were several stages to compile a program. Normally, the toolchain will combine those together to speed up the process, and here, we separate them out for you to see how each stage is manipulating our program. The first stage is called the pre-processing stage. In this stage, the compiler will resolve all the compiler macros we defined previously. It will go over the program and see where those macro symbols are used, and replace the symbol with the defined values. You can see that in the resulting main.i file, all of the macro defines are replaced with the definitions. The second stage is called the code generation stage. In this stage, all of the high-level C or C++ code will be converted to the RISC-V assembly language. The result is something similar to what you have written in your CS61C projects. The third stage is called the assembling stage. The assembly language will be further converted into binary instructions. The generated output is called relocatable object file, which is in the ELF formats, executable and linkable formats. So, what does these mysterious relocatable object file contain? These are binary format files, so we cannot look at the contents directly, but we can use the tools that the compiler toolchain provides to get a peek. For example, we can read the header information in our object file. You have learned the memory layout or program in CS61C, and you can see some familiar entries here. Do you still remember this diagram? The .text section is just text or program instructions, and all of these .data sections maps to the data block in our diagram. You can stack or runtime constructs, so we don't see them here. The remaining .comment and .risc5 attributes are for debugging purposes. We can also read out the text portion of the binary file and let the tool parse out the instructions. Note an interesting thing here. Because we are using the default compiler options, the compiler is performing some optimizations for us, and have used some compress instructions from the RISC-V compressed instruction extension to reduce the size of the program. But coming back to the previous one, the VN and del and A columns, which stands for virtual memory address and physical memory address, marks the starting memory address of each section. You can see that everything is 0 here, which is wrong. We cannot put everything at the same place. This is why we still have one stage left. The final stage is called the linking stage. The linker will combine different pieces of code and data together and figure out their correct memory locations to build a single binary file that can be loaded onto the processor memory. Alright, since it's already half Berkeley time, we will break here. We will come back to talk about the linking stage in the next lecture. See you next year.